I had the pleasure of looking around the park and seeing the dinosaurs just before sunset. I had been here before, ages ago, but it was lovely to see them. And of course, the friends of the Crystal Palace dinosaurs are here to make sure they're here in the future, because although the dinosaurs were big and robust creatures, their Victorian statues out there are quite fragile and they need constant loving attention if they're going to survive. And we start with one of those, and I think a strong link to the present day, of course, is the fact that this is what the experts in 1854 thought they looked like. And a question we might have is, how did they get it so wrong? But I don't think that's a good question. I think that's inappropriate, and I'll try to explain why. But just a little bit of background, if you're not familiar with the history of the Crystal Palace dinosaurs. They were the idea of Richard Owen, and we seem to have lost Benjamin Waterhouse Hawkins, I'm sorry about that, who was the sculptor. But Owen was a paleontologist. He was the dinosaur expert of the day. He was known to all the important people in society. At one point, he was tutor to some of Queen Victoria's children, and he knew Prince Albert very well. Some of you will know Prince Albert was very interested in science, and he was behind the museums area in South Kensington and the Great Exhibition, which took place in 1851, and from which these amazing dinosaurs come. And this was the first dinomania, because it wasn't just here are the models, but that was in itself something quite astonishing. The idea of actually trying to bring them back to life, which somebody like Owen must have found quite uncomfortable, because he was a traditional, classically trained scientist, and you're trained to be very careful about your observations, only write down what you can see, what you can prove. And for many people at that time, even today, they might say, this goes too far. You know, you're trying to push this. The evidence just isn't there. And so was Owen wrong? And this is to remind us that it wasn't just the models, that if you were a visitor in Victorian England coming to see them, you could buy a hand-painted poster or black and white print, or they even sold small bronze models of them. And so that the enthusiast could take one of those home. And I think the point is that our understanding of dinosaurs has changed considerably over the years. And Owen worked with the evidence he had, and he didn't have very much, it has to be said. So for each of those models, he probably only had 4 or 5 bones. He didn't have complete skeletons. But of course, if we mistakenly look back and say, oh, this is all nonsense and it's been updated, can we really be sure in 100 years' time whether what we're trying to do now will be regarded as any more correct than what he did? I hope so, but I can't say for sure. Now, what I want to do, though, is bring you right up to date. We're going to go back 25 years. Well, it's not right up to date yet. Back 25 years, and this is to illustrate something about the more recent history of paleontology. And 25 years ago in 1996, I was at a meeting of the Society of Vertebrate Paleontology in New York, and there was a buzz in the corridors because an article had appeared in the New York Times during the course of the meeting with the headline, "Feathery Fossil Hints Dinosaur Bird Link." Now, Owen would have loved to have known about this, but he just didn't have access to this information. And the science journalist, Malcolm Brown, wrote this thing, and it's an unusual article because he's making a big announcement to the world. We've got dinosaurs with feathers. That was the first, 25 years ago. But it was unusual because although it's derived from that meeting, he was not reporting a talk or a poster or a specimen that was officially on show. He was reporting a sort of buzz from the corridors. So what was going on? What was going on was that a Chinese scientist called Peiji Chen was from Nanjing. He was at the meeting and he had photographs of this little dinosaur here. He has this thing. And here's its head and the eye and the back and the legs and the tail. And it appears to have some sort of fuzz, some kind of tufty material all over it. And he was showing it to everybody at the meeting. And I remember then thinking, this is the first Chinese paleontologist I had ever met, because at that time, 25 years ago, China was still closed to the world pretty much. So the fact he'd got out was a wonder. And this is what Malcolm Brown was reporting, this thing here. And he was pursued by scientists and journalists. So what was going on? And I remember speaking to Phil Curry, who is a dinosaur expert from Canada. And he saw this thing and he said, there's something going on in China at the moment. This is New York. But at the same time, in Beijing, that month, October 1996, exactly 25 years ago, a paper was published with that title, Discovery of the Earliest Bird Fossil in China. So this was the first report of any such fossil from China. It was in Chinese, so this is the English translation, and this is a bit of the paper in English. And the people here, G and G, were describing this specimen, which was in the Geological Museum in Beijing. And they noted that it had a sort of fuzz of feathers and tufts and things like that, but they definitely called it a bird. It's in Aves Linnaeus, and in the title, Discovery of the Earliest Bird. And indeed, while he had been in Beijing the month before, Curry had seen this thing. And so he was beginning to put two and two together. Because there's something very, no, I should just say to finish the story, Pei Chen published his paper 2 years later in Nature, in English. It got big attention. The first one, remember, was in Chinese. But because the thing had already been named, even though on a different specimen, this is the Nanjing specimen, this is the Beijing specimen, this is the type specimen, this is AN other. So they were not able to name it. They just call it Sinosauropteryx, as had been the case. So China bird wing. But what's going on here? They look quite similar, don't they? This is the Beijing specimen. This is the Nanjing specimen. Guess what? The finder had very cleverly realized on splitting the rock open, we've got a single specimen, but we can sell it as two. And so the museum in Nanjing very happily paid an undisclosed sum. If you ask them, they won't tell you. And the museum in Beijing, likewise, with no knowledge of what the other was up to. And somebody, probably will never be known, very happily took the millions of renminbi to the bank. But importantly then, this was the very first feathered dinosaur ever known. And it was the beginning of a fossil rush from China. So I'll skim quickly over what we knew, because when I went to that meeting, this is what I knew. We didn't know about this Chinese fossil. All we really knew was Archaeopteryx. And of course, it has feathers, beautifully preserved from South China, picked upon very quickly by Thomas Huxley, who realized what it was. This is very important in our understanding of evolution. Found 2 years after publication of On the Origin of Species by Darwin. And of course, Huxley was Darwin's bulldog. Huxley supported Darwin and pushed and promoted his ideas. Darwin was quite a recluse by then. And so this was a perfect example to illustrate evolution. This is an intermediate fossil, and he called it a dinosaur in bird's clothing. And all we had, and I'm sorry my slides are being clipped a little bit, was dinosaurs at the bottom, Archaeopteryx in the middle, and modern birds at the top. And so that was all that was known. So the fossil record was very incomplete until these fossils from China. And so these are the kinds of localities where the fossils were being found. And I first went to China in 2007, so that's long after the first reports. By then, China was much more open. It was possible to get around. We could collaborate with Chinese scientists, and they took us out in the field. And we went to this is one of many localities, Sihetun, which has yielded 1,000 specimens. And the Confucius ornithids are early birds, and each of these specimens is as good as the Archaeopteryx. So many of us, certainly I was brought up, Archaeopteryx is the most valuable fossil ever found, worth millions of dollars. And now these Chinese localities are just producing dozens of examples. And this is what some of them look like. They tend to be rather complete. They often have feathers. They often have internal organs. In this case, the stomach contents of seeds. There's a whole range of other creatures and plants and so on, which I won't go through. but basically the Jehol fossils, the fossils from the Jehol group, which is the name of the rocks that they're found in, are all from ancient lakes. And the sediments are laid down in lakes. There's a lot of volcanic ash mixed in, and it seems that the ash, which would be slightly acidic, has helped somehow miraculously to preserve these extraordinary fossils. And you're getting creatures that live in the lake, fishes and mollusks and so on, as well as things like insects and birds that would be flying over the lake. And so here's Sinosauropteryx. It was the first to be named in 1996, the first feathered dinosaur ever reported. So if you think, oh, well, you know, the Victorians did it all, there's been big changes in our knowledge in the last 25 years. This is all new. And of course, the younger people, it's just there. It's in the textbooks, it's everywhere. It's in National Geographic, it's on television. But there was a point, and I saw the switch, you know, 1996, October. Up to that point, nothing. After that point, whoosh, just a gold rush of stuff. Here's that specimen. Here's an early reconstruction of the thing. And it was known to be not a bird. Of course, it is a dinosaur. It's related to Compsognathus, a small dinosaur from Germany. So there was no question. And this dinosaur, Compsognathus, is on the line to birds, but quite away from birds, quite a long way off. I'll come back to that. And here are the feathers. And so here's a bit of the tail and the tufts of things preserved in the rock. And they do seem to be in tufts of dark and pale. And so when it was described, there were many critics who said, no, these are not feathers. If it's a dinosaur, they can't be feathers because only birds have got feathers. And people say, well, yeah, but then, of course, birds evolved directly from dinosaurs. So where would the line be? Is it just by chance that because we found Archaeopteryx in 1861 and it's called the first bird, is that miraculously where feathers suddenly emerge? Because Archaeopteryx has got all the panoply of feathers that a modern bird has got, all the complexity of flight feathers and secondaries and primaries and all the rest, why would they not have originated earlier? And I think most people accepted that, but there were critics. However, those critics largely disappeared as more and more dinosaurs with feathers were announced. So 2 years later, Caudipteryx, very weird looking thing, clearly not capable of flight. I don't know what it's capable of, but at least there it is. And it not only has a fuzz of feathers as Sinosauropteryx had, but it's also got these more complex feathers with a central vein and lateral barbs and all the rest. And so it's much harder to argue that these things are not feathers and that there's something else altogether. And then Microraptor 2 years later, the most extraordinary thing, and this is another one that will come back in a moment. It has got all the range of feathers that you see in a modern bird, as in Archaeopteryx, but it's not a bird. It's on a separate branch in the evolutionary tree. And not only that, it's got 4 wings. So this was something people had speculated about. Oh, and the image has disappeared. But nonetheless, there have been many birds discovered as well. And I mentioned Confucius ornis, wonderful Chinese name, and thousands of specimens of this thing have been found, including the picture I had there, which I regret has been clipped off, was of a male and a female. And the male has got long banner-like tail feathers. So that was something else that we were not expecting. But then you've seen the wonderful David Attenborough films about lyrebirds, and they jump around and the male does this and that. And they were doing that 150 million years ago in the Cretaceous. The males were hopping around and waving their tails, and the females presumably were sitting around looking bored. But so that it's adding knowledge, but it's filling out the tree. So I showed you a diagram a second ago where it was just really dinosaurs, Archaeopteryx, and modern birds. Now we've got a huge plethora of additional information filling out that tree. And the detail doesn't matter too much. Here's Archaeopteryx, here's modern birds. There's lots of fossil birds. There's now all of these dinosaurs, feathered dinosaurs, on the way to birds. And it's possible to look at the evolution of the wing, because some of those dinosaurs have a wing-like structure, but which is clearly not capable of powered flight, because the area of the wing has to be large enough to enable the thing to get the weight of the body off the ground. And clearly the bigger the bird, the bigger the wing. And indeed, the area of the wing is proportional to the mass of the bird, which is why a little bird like a sparrow has little wings. And if you scale the sparrow up to be much 10 times heavier, the wings have to be more than, well, they've got to be 10 times the size to support the weight. Oops. There was an evolutionary tree there. I'll just hop past that. Oops, and here's another one. So I'll say this. So I'm sorry. This is a very smart gizmo. I just put my pen drive in the back. There's not even a computer there, but now I see it's not entirely foolproof. So I can say this, though. So we saw Microraptor a moment ago. I'll pop back to that. And the point was people were calculating who could fly and who could not fly. And it turns out, in terms of powered flight, it turns out Microraptor could, because the calculated area of its 4 wings is quite sufficient to lift the body off the ground and to flap and to power itself through the air. So we're learning, not only filling gaps, we're actually learning that birds were not the only derived dinosaurs to attempt flight. In fact, it turns out there were 4 or 5 different groups of these dinosaurs that were getting off the ground and using different means. So Archaeopteryx and its ancestors used the single forelimb wing. Microraptor and its relatives were using 4 wings. Well, why not? You know, it's another way to do it. And there's another one not illustrated here called Shi Yi, which had a sort of bat-like wing, a membrane wing, and it was capable of flight as well. So there's a variety of these little dinosaurs that we now know, thanks to those rather simple calculations, are capable of flight. Whew, I'm glad this one is here. So we get to dinosaur color, because this is the purpose of the book. The book has 2 purposes. It's probably got more, like the Spanish Inquisition. 4 purposes. The first purpose is to talk about color. How do we know the color of dinosaurs? I'm going to reveal that now. And secondly, to show how we believe we can represent these ancient creatures without the use of a time machine. So that's the important point. Richard Owen began it. We may smile at his efforts, but he was doing what he could. We now have a great many more specimens, including these astonishing things from China, which for him were entirely unavailable. So 11 years ago, we published this paper, and note the word melanosomes. They're the key. I'll explain what they are. But the rest of it, we're saying we've got the color of dinosaurs. And this is Nature. That's an important journal to get these things into. And this was a group from China and Bristol who did this. And just to be really clear, well, first of all, of course, it created a great deal of excitement at the time, our little beast over there. And not only that, unknown to us until the last minute, a team at Yale as well were after the same thing, and they published 6 weeks later. Not that it matters, because it's all 2011. And what we were both saying, and this is our beast, Sinosauropteryx, which we've seen from the start, that this reconstruction on the left is incorrect, and this one on the right is correct. Not because I say so, but because I have got evidence to show you. And that's the key point. And the evidence consists of melanosomes. So inside hair of mammals, including humans, and inside feathers of birds are these structures called melanosomes, which are sort of hollows or capsules within the structure of the hair or the feather. And they are the means by which pigments get into the hair or the feather. Because hairs and feathers are made of a protein called keratin, and that's the same protein that makes your fingernails, and they show the natural color of keratin, which is transparent. And my hair is the natural color of keratin because I have lost pigment from my hair. And yet in the colors of, many of the colors of birds and all the colors of mammals come from 2 versions of melanin. And so melanin is a well-known pigment that occurs throughout all of life in many contexts. It's not just there for external color, but it's also, for example, forms the black of the retina of your eye, so it enables you to see, but also it's inside organs like the liver and the spleen and various other things inside. But to get into the plastic-like structure of the keratin, the pigment can't just insert itself randomly and somehow mix into the keratin. It's enclosed within these capsules or small structures, which are each about a micron in diameter. And it so happens that the 2 kinds of melanin, the eumelanin gives the blacks, browns, and grays. That's the common kind. And the pheomelanin gives ginger colors, hence the diversity of hair color that you see in humans and in squirrels and other mammals, and of course many of the colors of birds. And so this zebrafinch shows both types, and in the ginger patch on its cheek, that's pheomelanin. The pheomelanosomes are spherical, whereas in the eumelanin areas, the eumelanosomes are sausage-shaped. You maybe can't quite see that. The photograph maybe isn't quite clear enough. That's the secret. And those shapes are preserved inside the fossils. So we were able to take a feather structure from Sinosauropteryx, crack it open, look at it under the scanning electron microscope. This is what it looks like. This is the fossil. It's got spherical structures in positive, but mainly in negative, because of course these things are embedded into the plastic-like structure of the keratins. So we're seeing a moldic appearance here. So we compare back with our indicators from the modern example. They're like the top one, pheomelanin, hence we reconstruct ginger. And we looked all over the skeleton. And I can say when you go to the curator, there's a language problem, not least, of course, in China. But with our translators, we explain, we know this is your prize specimen, which is worth tens of millions of dollars. We have a small scalpel here. We would just like to take off a little piece, scratch another bit here, I know the feathers are the key feature that people want to see. We're just going to scratch a few of them off. And we did sample all over the body because we wanted to be sure we were not missing anything. So that's it. And this is what we call a chain of inference, or you can call it evidence. And so this is classic scientific research. This is pure science in the sense that it can be rejected. It is testable. So anybody else who cares to can look at another specimen of this beast, and they can take their own samples, they can make their own observations. Or they could seek to disprove it by looking at lots of feathers of modern birds. So how can we use it? We can use it because, of course, this is common to all birds and all mammals. So this relationship of color to form is common to all birds and mammals. It wouldn't work if it was simply zebra finches or if it was simply birds. Because if it's simply birds, you might think, well, dinosaurs are ancestral to birds, therefore why would they not have the bird characters? Dinosaurs do not have all bird characters. What sort of singing do you think T-Rex was capable of? Just because a blackbird sings that way doesn't mean that its distant ancestor did. So we use this principle of bracketing. We don't just follow down a line. We actually follow down the line to the ancestor and back up again. And so in the evolutionary tree of vertebrates, birds are over here, mammals are here. And if they both possess this unique relationship between pigment and the shape of these organelles, then everything back to that ancestor did as well. And then everything included within that tree. And that includes dinosaurs and all these other fossil creatures. So that's our argument. It has, you have to develop the ground very carefully and be sure that you've got that right. Now we have this could be disproved, but we've survived so far for 11 years, and so since our paper, maybe 500 or 600 further papers have come out, all following up and looking at other species and using the method. And so I think you can buy the book with confidence. We're all right. I could have written this 10 years ago, but it would have been much more on the edge, and people could have said, nah, this is an untested idea. And so this is the Bob Nicholls reconstruction. So a key feature of the book is that Bob Nicholls, who is the best paleoartist in the world now, I think, he produced these digital images, 15 new images for the book, where you can look in as much detail as you like, and every feather, every hair is shown. And so this is based upon what we did plus later work. And so this, we would argue, is the nearest to what the dinosaur really looked like. So here's the book, and it's not published September 2021. And so I'm going to just tell you a couple more stories, and I'll keep an eye on the time. I won't go on forever. I'll try and stop in about 10 or 15 minutes. And so the next story is about Psittacosaurus, which is another Chinese dinosaur, but very different looking. This is a plant eater. This is a parent with some babies, and there are lots of fossils that show that occurrence. So here's a fossil of 6 babies of Psittacosaurus, which one of my students, Zhao Qi, studied a few years ago. And because he was a member of the museum that this came from, he was allowed to do another scary thing, which was to cut through the bones and look at the bone histology under the microscope. And again, if you or I were to ask, we'd be told, no, you can't do that. Because in reptiles, you can actually, with a fair degree of confidence, tell their age by growth rings within the leg bones. So it's almost like a tree growing, almost. They add rings. And we wanted to know, are all of these the same age? And it turns out they're all 2 years old, except for the pink one, who's 3. And for some reason, this looks like a little family group, except for this older sibling. And they're occurring in ash. So this is from a locality called Lugiatun, which is in volcaniclastic sediments. And it's sometimes called the Chinese Pompeii, because the dinosaurs seem to be preserved just almost in life posture. And in this case, in some sort of association where we fancifully imagine they're all pointing the same way because they're running away from the hot ash that's falling on them, and eventually they succumb. That fossil, unfortunately, does not contain any soft tissues like feathers or skin or anything. That's all been burnt off, as with the humans and dogs at Pompeii. However, an adult specimen of Psittacosaurus was preserved in the lake sediments, and there the whole body outline, the skin, this is the head end and the tail end and the legs, and all of this is skin. And on the top of the tail, you probably can't quite see it, there are weird kind of reed-like marks in the rock. And so, we have it anyway. So forgive me, I did have a set of other images, but I'll just focus on this one. When Bob was reconstructing this one, it does have feathers, these weird things on the tail. What can I say? They are some sort of keratin-like structures. Call them feathers if you like, call them what you like. But this pattern of dark on top, pale belly, and the speckles on the front of the shoulder and so on, that's all there in the fossil. And those colors, those speckles, are melanins, so they are recording, they're preserved. And melanin is a very tough molecule, I should have said, so it's not a surprise that it actually can survive in the fossils. So this is another reconstruction that is based on some exquisite specimens, like I showed you a second ago, and with behavior shown from the babies. We don't just talk about dinosaurs. It's been noted, of course, the title of the book is Dinosaurs, and yet that image on the cover is not a dinosaur, it's a pterosaur. And so the flying reptiles are close relatives of dinosaurs. And indeed, we studied this one a couple of years ago, and we were looking in particular at the fibers all over the body, and it had been known, well, pretty much from the days of Richard Owen, in fact, from the 1840s and 50s, that pterosaurs had some kind of a fuzz of insulation. But these were called pycnofibers, so they were not confused with hair in mammals, birds, feathers in birds and dinosaurs. And this happy-looking little pterosaur here is the one we looked at. And what we found was that the hair-like structures, the pycnofibers, actually, many of them are branching. So in this paper here, we identified 4 types. And our argument was, well, if these things are made of keratin, if they contain the color pigment in the way that feathers do, and they are branching, then they are feathers. And indeed, these 4 types shown here in the cartoons, we also can identify in different dinosaurs and in living birds. So they wouldn't let me get away with pterosaurs had feathers. I wanted to just be really clear. But we've just said complex feather-like branching. Anyway, the journals always want you to be careful and measured and conservative. But again, so this is only 2019, so 2 years old. We could be blown out of the water on this one. But nonetheless, even if they're not feathers, I think they are, but even if they're not, we've got the colors because they're full of melanosomes. And here's Bob Nicholls' drawing of Anuognathus, that middle Jurassic, small size, it's about the size of a pigeon, and looking very happy, as you can see, because it's spotted a nice lacewing that it's going to eat up. And it's got a nice whiskery face so that it can trap insects. But what about some of these later pterosaurs? This one here, Tupandactylus, is just one example of a Cretaceous pterosaur. This is huge, and it is completely crazy looking. The fossils are from Brazil, so it's not a story about only stuff from China. But when you look at the whole skeleton of this thing in a museum in Brazil, if I can just try and orient you a bit, this is the head and the neck, and then these are the hands of the wings. So these are the wings kind of folded up. And then at the back are the two hind legs. And so the thing is standing up quite high on its hind legs. It's got its wings on the ground with the hands on the ground. And this crazy huge head, which has got a long, hollow, bony part going back, and then a thin, thin strut, just like the front of a sail on a very lightweight sailing boat. And the fossil there, which I hope is in the next image, is here. So here's the skull. I mean, you'd hardly know how to work that out at all. This is the front of the mouth. It's got no teeth. There's the strut. And in the fossil is this preserved sort of skin. And it's not been scratched by somebody with a chisel. These lines represent folds in that sail. And on close study of that structure, melanin is found, and it seems to occur in a speckled kind of pattern. And there's another reconstruction, the one by Bob Nicholls on the book. And it was even suggested that perhaps some of these structures in the membrane had luminescent properties, meaning that they could somehow pick up energy from the sunlight in daytime. And then something like a firefly, they could actually release that energy after dusk and somehow flash their crest in a remarkable way. And so here's the reconstruction and showing that kind of speckled pattern all over the head and wings. And tightly covered. And this thing, I should say then, has a wingspan of maybe 5 meters, 15 feet, 15, 16 feet. So these are not trivial creatures. So the final story is a very different kind of dinosaur, this one from Canada, from the Athabasca tar sands. You're looking at a very distant shot of these enormous and rather hideous looking locations where they literally strip off the sand and squeeze out the oil. It's just absolutely full of oil. And a number of years ago, 10 years ago or so, a 1-ton huge skeleton was found. It was quite unusual to find anything much there. And here it is, and it was named Borealopelta, Boreal meaning northern, Pelta, something about the armor. And this is an armored dinosaur. The head is pointing towards me, and the neck is surrounded by rings of bony plates, and then the back of the thing heading out the back, and parts of it are missing at the back end. And so we're just looking at the front end of the thing. But it's got this very all-encompassing, all-including armor. And you wouldn't think, does this thing have feathers? Does this thing have any color? And it's pretty huge. So the paper was written, they did a very detailed study of the armor plates. So here's the head end, and these different rings of bony plates. They are solid bone, and some of them quite spiky. But indeed, these bony plates in life were covered with keratin. Because if you think of the antlers of a deer or the horns of a cow, of course, cow horns have a bony horn core. The antlers of deer tend not to because they can shed them completely. But the antler is made entirely of keratin. The covering of the cow's horn is made of keratin. And sometimes you'll see the sheath of the horn coming off. There is no case, I don't think, where any vertebrate will have exposed bone because it just can't. The bone would just rot. It just can't survive against the air. And so they're always covered in keratin. And indeed, the keratin covering the scales, you can see a pinkish color at the back, contained a lot of pheomelanin. So we know that this big beast was quite gingery. Here's the reconstruction. And so don't think of this as an amiable little tortoise that you could sort of hold on your hand. This thing is more the size of a Sherman tank. It would weigh 5 or 6 tons in life. And its armor is clearly there for a purpose, including these scimitar-like blades, which are each 1 meter long. And when covered with keratin, they would certainly cut your finger off or cut your leg off if you came against them. So like the scythes on the wheels of Boudica's chariot. I don't know if there's any truth in that matter, but nothing is new under the sun. The dinosaur already had them. And it would be attacked by things like T-Rex, and of course this would be a tasty morsel. It would normally defend itself like a turtle does by tucking in and just hunkering down, and the dinosaur, the predator, would soon give up. Okay, so what I'm going to do is just skim to the end here and just say we can identify, I'll go back to the summary. We can identify a bunch of different things about color, speed, bite force, feeding, growth rate. So there's a whole range of things that in Owen's day were quite speculative, whereas now we can talk about many of these phenomena based upon evidence. And the hardest of all, before you came in, if you didn't know the story, the hardest of all you would have thought is color. How on earth can we know the color? I've shown you how. And we can determine speed by looking at trackways. I won't go into the detail. Or by looking at estimates of the muscle volume. We can determine bite force from actually bitten fossils. So this is a piece of Triceratops bone that has been bitten into by T-Rex. And so by measuring the depth and the force required to insert your tooth 3 or 4 centimeters into the bone, you can work out the bite force, or by 3D digital models. I won't describe this in any detail, other than that this is the kind of work that modern computing allows us to do. Emily Rayfield here, my colleague in Bristol, applies finite element analysis. And just a thought to leave you with on this, the color thing, all right, I see how you do that. Bite force and these kinds of stress strain diagrams. If you've ever been in a skyscraper building or in an airplane, you have given a vote of confidence to finite element analysis. You maybe didn't realize it, but in doing that or going across a modern bridge, you're giving a vote of confidence to FEA. Because every modern structure is first designed in the computer by engineers using this method. And it's a way of, you determine the materials, you label the materials, and you know the properties of those. And you can therefore test that aircraft, and it behaves differently if it's made of steel, or if it's made of wood, or cheese, or whatever you decide to make it out of. And you can quickly decide, right, we should make it out of this, or this, or this. So, and she applies them to dinosaurs, and it works, because we know it works. And so this is the book, 15 stories, and I suppose there's a serious message behind it. Paleontology is a science. How do we do it? We're not magicians. We are just regular people making observations, making arguments. But it's pure science in the sense of being testable and rejectable, and in being, what's the word, provisional. Science is provisional. We've heard a lot of this through the coronavirus times, of course. Why can't you scientists just give us the facts? We're giving you our correct information as good as it is today. But we can never say this is an absolute fact that will never be shown to be wrong in the future. Just think Newton, Einstein. You know, Newton was not a fool. Newton got a lot right, but Einstein understood even more. And I'm not suggesting that dinosaurs are on that level, but nonetheless. And so times change, we acquire more information. We hope that we're getting it right. And so if you're interested in some of those topics, I'll be very happy to answer any questions. That's it. Thank you.
Thank you. That was spectacular. Thank you.
Thank you.
I think we can take questions. Anybody up lights a little bit? Anybody have some questions about spectacular dinosaur colors and how we know them?
Sorry.
Thank you. Yes, please.
I know there's been some theories related to the cries and the sound they make, and I know it's all related to soft parts.
Yes.
So where are we on that side?
Yeah, so
it's purely speculative, or do we have anything?
Well, so the question is about the noises that dinosaurs made. And that's a nice question because you look at their living relatives. On the one hand, crocodiles. On the other hand, birds. Doesn't help much, does it? Because they can make every kind of noise between them that you could possibly imagine. But there are some dinosaurs which I didn't talk about tonight, the duck-billed dinosaurs, which have crests on their head. And those crests have got the breathing tubes from the nostrils going right into the crest and back down. And when people realized that, they were able to model the shapes of these structures, line them with a kind of mucous membrane, because in life, of course, they would have had a soft tissue, and then blow into them like a trumpet. And indeed, they do make interesting trumpeting noises. So at least amongst the duck-billed dinosaurs with all their crests and so on, they were probably trumpeting and tooting. And the males and females, in certain cases, appear to have different shaped crests, so they might have been a beep and a beep. And the babies had different shaped ones. So there'd be all sorts of little noises at different levels, and depending on the shape. But as for the others, regrettably, we've got no idea, because normally if you're just making noises from the throat or whatever, none of that's preserved. Thank you. Yes, thank you.
You could only seem to identify a limited range of colours, the sort of greys and gingers.
Yes, that's right.
Is there any evidence for other colours?
Great question. I slipped past that and hope nobody would notice that birds also have other colours. And so mostly the other colours come from things they eat. And so there are colours from carotenes, which are like in flamingos, pinks and yellows and so on. And then there's colours from porphyrins, which they give purple and green types of colours. So these are things in the diet, and somehow they can insert into the feather. If you think of flamingos at the zoo, one week they're pink, the next week they're not. It depends on what they've been eating. And so clearly the colour can go in and out. And so I've got no idea how that works. And regrettably, we can't yet detect that in the fossils. But people are working on that. There are fossil carotenes certainly known in plants, and I think people are keen to try and capture that if we can. Thank you.
So
oh, sorry, I think the question, yeah, I'll come to you in a second, yeah. Yeah, thanks.
I was going to ask, feathers are extremely complex
Yes.
structures. If they did evolve those for flight initially, then why did dinosaurs need feathers?
Yeah.
And also, do you think it's possible that all dinosaurs basically have feathers?
So feathers are highly complex, you're quite right. But the simplest ones, as in Sinosauropteryx, are just a single hollow tube, just a single bristle. And they just come out of a little follicle in the skin and they just grow, and that's it. Whereas, of course, the contour feathers and flight feathers have the more complex structure of the central rachis, the quill part, which is a hollow keratin structure, and then the very complex interlocking barbs and barbules at the side. So we don't know how those evolved. We simply know that lots of dinosaurs had them. And it looks as if pterosaurs as well. So that brings me to your second question, which is indeed we suggest that feathers originated with the common ancestor of dinosaurs and pterosaurs. And so something like 250 million years ago. So that's 100 million years before Archaeopteryx. So one result of all of the new Chinese fossils, in a sense, has been to push the possession of feathers out to nearly all dinosaurs, as well as close relatives, and the date of origin from 150 million years ago, late Jurassic, which is Archaeopteryx, to 250 million years ago. So it's a big shift of knowledge. And the functions were initially, it's assumed that hair and feathers initially are for insulation, and they can have a secondary function in flight, and they can have a secondary function in display. And so what this has shown us is insulation first, yes. So the very early ones, the early mammals, the early birds would have had their whiskery coverings for insulation. But it seems that at least these dinosaurs and pterosaurs, they started using them for display quite early on because they started having color patterns, which we've not yet found any color patterns that you could convincingly say are camouflage. They tend to be specifically in the tail, in crests and things like that, which suggests they're for showing off. Thank you. Yes, sorry, you had a question.
Where did so dinosaurs never had scales, or is that?
Oh, they did. So, and that, yeah, part of the other question was, so we don't know feathers from all dinosaurs. Many dinosaurs had scales. And scales and feathers are essentially the same thing, really. So they're all made of keratin. And in terms of development of the embryo, the early bird in the egg, the little baby, the tiny, tiny early chicken inside the egg has got no feathers. It's got scales. And then as it develops, the feathers sprout. So we're seeing the sort of ancestry being played out to some extent. And mammals keep scales as well. If you think of the tail of a rat, you know, it's kind of scaly. The legs of a chicken, they're scaly. And so lots of birds keep scales today. And lots of dinosaurs had a kind of mix of scales and feathers. And in some that we know, Colindrodromaeus, which I didn't talk about, from Russia, the detail is fantastic. You can see different kinds of scales on the legs and the tail, different kinds of feathers in different parts of the body. Quite amazing. Yes?
I was curious about the colour of the modern bird as well. So if you were to analyse a parrot or something purely on the basis of melanosome appearances, would it in fact be quite dull rather than bright?
There's a third kind of colour that parrots sometimes have and certain other birds, which is iridescence. And so that's the mirror-like property that the feathers of certain birds have, and particularly kingfishers, for example. So I think if you did the reconstruction carefully with a knowledge that iridescence can be caused when the melanosomes are lined up in layers, and they form a sort of reflecting structure that would have given, and so certain dinosaurs also had that iridescence as well. So I think we could reconstruct the colors and color patterns of modern birds just using this kind of method, but we would be missing the carotenes and porphyrins, which give you those additional colors. But they don't tend to interfere. So if you're getting, so with the flamingo, for example, it's essentially all white. It's got black bars on the wings, which are melanin, but the pink occurs in the white. So the pink occurs where there is no melanin. So with any of the fossils, we would be predicting other colors only where there is no melanin. And even in a complex pattern bird like a mallard or certain ducks and so on, where they have a mix of everything, lots of black, lots of white, lots of brown, lots of purple, green, the areas of purple and green are very definitely set off and rimmed with melanin, but the feathers would be blank otherwise, and then the other pigments fill in. So they seem to be somehow very clearly delimited into different parts of the feathers. Oh, yeah. Oh, yes, thank you.
Yes. Birds have a larynx, but did dinosaurs have any larynxes?
Birds have... Oh, larynx, good grief. Well done. Yes. Yes. Thank you. No, that's a fantastic question. And I thought I heard that, but I just wanted to be sure. I don't know the answer, but I would say almost certainly they did. And what's the larynx for? It's for the voice, isn't it? Yeah. So, and I think in us as well. And so they must have had something of that kind, because we must imagine these great dinosaurs were honking and shouting at each other in some way. But I'm very sorry that we don't find them in any of the fossils. What a fantastic question. Thank you. I didn't know about that at all. I'm going to have to go off and read about it myself. Oh, yes, Ali.
Generally, how much can you infer about the behavior of extinct animals from fossils? And do you feel like sometimes it's a bit too conservative, or paleontologists are able to...
Yeah. So the question is about behavior. I think behavior is a broad, sweeping thing. So we can infer a great deal about behavior from the fossils. So, for example, there are many dinosaur nests which are full of eggs. So if you would say that nesting behavior and bringing up the babies is part of behavior, that can be documented by fossils. We can say, well, this species of dinosaur excavates a nest like this. The nests are on the ground, by the way. They didn't nest in trees, I think you can understand. And you know the size of the nest and how many eggs they lay, and in many cases the embryos are preserved inside. And just the other day, a new nesting site was announced from Argentina, where there were nests and juveniles and adults and lots of crowds and crowds of individuals. And the nesting sites were spaced one dinosaur length apart. Just like if you look at a gannet colony or any bird colony, they seem to be close together, but they're actually just far enough that they can just about peck each other, but not cause serious damage. And it seems the dinosaurs were doing on a bigger scale. You know, a gannet is what, that's a meter or more, but these were like 10 meters, but they could sort of bite each other, but they couldn't destroy each other's nests. So, and we would speculate about sexual selection behavior because some of them have these wonderful crests and tails, but that's much more speculative. If you include locomotion and feeding in behavior, then of course we have fossil trackways that show you exactly what the footprints are like, and you know who made them in many cases because of the shape and size of the hands and feet, and the spacing of the tracks, the stride length gives you the speed of movement and stuff. And feeding, of course, there are examples like I showed of pieces of bone or other things with tooth marks, and you can tell from, you take a mold of it, oh, that's a T-Rex, you can tell who bit. So we can piece together quite a lot about dinosaur behavior. But I would always want to do it in that kind of evidence-based way, rather than just saying, well, I think they were all very good parents. And you have to say, well, okay, yeah, can you actually explain more about that? You know, because that's just...
Isn't that what happened with a lot of dromaeosaurs? So they assume that it would be like wolf pack, and more they tend to think they might just have been hunting small prey.
Yes, yes, so you're right. So in certain cases, the predators are much smaller than the potential prey, therefore pack hunting, and there are some... Exactly. So there are cases where you can use a bit of biological common sense, but you should use the fossils where you can, I would say, I think. Thank you. Yeah. Yes, thank you.
So obviously when you get a fossil, it's at a point in time.
Yes.
Do you have any evidence of colours reacting to the environment? So like hairs in the Arctic changing from white to brown?
So the colours matching the background or having some role...
Just changing to the environment.
Oh, I see. Yes, yes, yes. No, that would be far... Yeah. Gosh, it would be lovely to think. I was going to say, well, there are cases of camouflage in the sense of counter shading, but I don't know how we would ever find from the fossil if they could change colour like a chameleon or something like that. There are bits of, there's a fossil snake where people have suggested that, much younger, maybe 30 million years old, which they've identified iridiophores, and I can't remember the names of all these special cells in the skin, where they would argue these are the sorts of cells that allow color changes, because they're very special cases where you have a bunch of cells that can expand and contract. And of course, when you look close up, you can see these fishes and lizards and things changing color by the little points of black just get bigger and bigger and bigger, or the little points of green swell up, and the whole thing then changes color. I don't think we have any fossil skin that would be good enough to show that yet, but who knows? Yes, thank you.
If there was a gap, so there's a huge gap in between.
A huge gap,
what
yeah.
we thought
Yes.
was in 1854. How big was the gap?
How big was the gap? This is with missing fossils. The gap was about 75 million years, which probably isn't enormously helpful, but I could say the gap has been filled by 10,000 specimens. Maybe that's a better way to think of it. So in 1854, we had nothing. Now we have 10,000 specimens. So it's filled the gap very nicely, and given us a huge amount of information. And those 10,000 specimens maybe belong to 100 different species. So it gives us a lot of information. Oh, yes. Oh. Were some dinosaurs iridescent? Yes, they were. So Microraptor, definitely, you should look up Microraptor. That's your hero dinosaur. And I think when they first looked at Microraptor feathers, they were all black. And then they noticed that the melanosomes were arranged in sort of sheets. And so yes, the feathers were black, but they also had a fantastic flashing quality. So when the animal was moving, it would sort of appear and disappear, and it would kind of flash, reflect, and so on. So yes, they were. And we can actually see that in the fossils. Thank you. Yes, it's in the book. Thank you. Yes, there's a whole chapter. Thank you. Oh, Ben, thank you.
Mike, you talk about China opening up being sort of a real game changer in what was available, where they found fossils. And what else is out there? Where's left that we don't know?
There's probably lots more in China because much of the country is not being explored as thoroughly as it could be. And sometimes people think, oh, China must be somehow miraculous because it's just generating all this stuff. But basically what we've seen has been they've compressed into 25 years of discovery what had lasted for 250 years in Europe. So all the wonderful fossils from all over Europe have come out, including from this country, Germany, all sorts of places. But yes, there must be lots more to be found in China. There's lots of remote parts with rocks of the right age. And people are finding some amazing things in South America, for example. There's big areas there that haven't really been explored yet. So we would hope for more from Australia as well, but I think people have been looking quite hard. Most of the rocks are much too ancient, so maybe not much more there. So, but regrettably, there's no way of predicting what that next thing will be, because who would have ever predicted any of this 25 years ago? And now the world has changed.
Thank you. I think at this point we should thank Mike for an incredibly stimulating and beautiful talk. I was just realizing that this is the first in-person science talk that I've heard for over a year and a half. And this is an absolutely wonderful way to open our minds and curiosity up again to all the wonders of paleontology and hearing about the forefront of dinosaur science. So thank you to Mike, and thank you to all of you for your excellent questions and for coming out on this night. And I hope it opens new ideas and new ways of seeing our dinosaurs here in Crystal Palace and the rest of the dinosaur world of discovery that's out there. So thank you again, Mike.
Thank you. Thank you.